Hello, and welcome to Below and Above, Storing Carbon in the Pennsylvania Landscape. My name is Meredith Graham. I am an environmental professional and vice chair of the Conservation and Natural Resources Advisory Council, known as CONRAC. CONRAC is a bipartisan advisory council that was created in 1995 by the same legislation that created the state agency known as the Department of Conservation and Natural Resources, or DCNR. CONRAC members include the Secretary of DCNR, Cindy Dunn, and 18 citizen members who are appointed by the Governor's Office and both houses of the General Assembly. We conduct public meetings every other month, and we undertake various measures to assist the agency. One of our goals as an advisory council is to create conversations between the department and the public around particular topics of interest. Hence why we call this kind of program CONRAC Conversations. Today's webinar is part one in a series about storing carbon in the Pennsylvania landscape. The focus of today's session is underground carbon storage. I'll be sure to invite you to part two of our series at the end of this presentation. With that background, it is my pleasure to introduce our panel of speakers. Our first presenter will be Kristen Carter of DCNR. Chris is a professional geologist and currently serves as our assistant state geologist. She has developed technical expertise around a variety of topics over the course of her 30-year career in both the public and private sectors. Most notably, as you'll see today, Chris is well versed in the ins and outs of carbon capture, utilization, and storage, or CCUS. She leads the Commonwealth of Pennsylvania's CCUS Interagency Workgroup and is a member of the Biden-Harris administration's CCUS Non-Federal Lands Task Force. Our next presenter is Jacqueline Fiddler of Consol Energy. Jackie has 18 years of experience with Consol and is currently the Vice President of Environmental and Sustainability. Consol is a Pennsylvania-based producer and exporter of high-quality bituminous thermal and metallurgical coal. As you'll learn today, Consol has undertaken significant investments in the areas of advanced carbon materials, waste coal utilization, and greenhouse gas emission reduction technologies. Our third and final presenter is Perry Babb. Perry is the president and founder of Key State Energy, the company that is leading the development of the Atlantic Coast Clean Hydrogen Corridor. This corridor currently includes revolutionary natural gas synthesis and carbon storage projects known as Key State Pennsylvania and Key State Virginia. Perry has more than 40 years of organizational development experience and has founded multiple successful companies and nonprofit organizations. I have a few housekeeping notes before we begin our presentations. Please note that this session is being recorded for training and record-keeping purposes. We will have a brief question-answer session after each presentation. Audience members are in listen-only mode, so we ask that if you have questions, and we encourage you to ask questions, please use the Teams chat function to type your questions for our speakers. We will also invite you to ask questions of the entire panel at the end of the program if time permits. Finally, on behalf of CONRAC, thank you for joining us today. We hope you enjoy the program. And with that, I'll turn it over to Chris.
Thank you, Meredith, and welcome everybody. It's great to see all these familiar names and faces on our call today, including some of our colleagues from that interagency work group that Meredith mentioned in the introduction. Let me get my sharing going. Okie doke. So you should see my title slide now. I guess John is still having some trouble with his volume, but I do believe I'm being heard by everybody else. So let's get moving. Happy to be with you. I'm here representing our Bureau of Geological Survey, which is one of several bureaus within DCNR. Those of you who are, excuse me, familiar with our CONRAC group, the survey routinely reports out some of our technical research, and this particular one is a topic that is top of mind. So my contributions today, I'm kicking us off. So I'm going to tell you some of the technical and logistical things regarding CCUS. And more specifically, I want to hit on these 3 questions. I'm going to tell you about what it is, how CCUS is related to other things that you may be hearing about in the news these days. We're going to define geologic storage, and I'll explain why that's important. And finally, how the Commonwealth, how Pennsylvania's geologic natural resources can support the state's energy infrastructure. So let's start with the terms first. CCUS. So it's the umbrella term that refers not only to technologies used to capture carbon emissions, whether they be CO2, methane, which is CH4, or others, utilization efforts, so taking those carbon molecules and doing something productive with them, as well as storage, so sequestering the gathered CO2 and putting it underground by way of injection wells and porous subsurface rocks. So we're going to be talking about utilization as well as storage today throughout my presentation. A related term that you've bound to, have heard in the news is energy transition. A textbook definition of that is given on my slide there. It's essentially cut and dried. It's a change in the way the energy system works because of some economic driver or combination of economic drivers. However, I think that many of you would probably agree that when we, as a scientific and equitable community of citizenry here in the United States, think about energy transition, it's not just the economics. So we are looking at a significant structural change in the energy system, but it's not just driven by economics. We're not running out of domestic energy resources. Our shale gas resources here in the Appalachian Basin are phenomenal. Our coal resources are still being utilized. So it's the desire to change how we get our energy and in what combination we get our energy resources, because we want to decarbonize our world. We want to be proactive in mitigating climate change. We want to promote environmental justice and the equitable access to energy resources. And we want to do all that in combination with the fact that our population across the globe is growing each and every day. So we don't want to just make it equitable for everybody. We want to make it equitable for everybody, and everybody that is to join us here on Earth. So, and all be prosperous, and without giving anything up. So that's a very tall order. You may have heard different environmental justice or equitable conversations in the news, like the sustainable development scenario. CCUS is one of those technologies that's needed to support the SDS. And as you can see from the graphic, this particular scenario is focused on addressing climate change, achieving universal energy access, so bringing everybody up to the same level, and in the process, improving air quality and our environment in general. The SDS, if as it's implemented, it's intended to reduce CO2 emissions while tackling all of the air pollution and other related environmental concerns. One thing I want to make sure everybody understands is that there's no single or simple solution to reach sustainable energy goals, regardless of which one you're looking at. So this particular graph from the International Energy Agency looks at over the decades. On the x-axis, the y-axis is gigatons of CO2 emissions per year. If we just keep doing and living how we're living now, current trends, the red line is going to take us higher and higher in terms of CO2 emissions, right? So we do nothing, it'll continue to go up. There are some existing stated policies on the books, whether domestic or abroad, and if we hold ourselves to those, we could potentially flatline emissions. So that's what that blue stated policy scenario is. The sustainable development scenario is the thing that is intended to take all of these different technologies, existing, fledgling, or well documented and proven, and use them in concert to reduce global annual emissions of CO2. So it's not just efficiency items, it's not just renewable energy resources, it's not just switching fuels or using CCUS or other things. It's the combination of those approaches, depending on where you're at in the world and what makes sense given your geographic location. And I would go so far as to add this particular graph specific to industrial decarbonization, excuse me. Especially when it comes to Pennsylvania, we have industries that are hard to abate or harder to decarbonize, and changing the fuels that they use to run their plants to make their products is not going to solve it. As a consequence of the industry or the manufacturing that they're doing, there is CO2 that's going to be a waste stream that they have to deal with. So again, efficiencies, CCUS, all those things together should be included as a portfolio of approaches. And many of you have seen this a chart or a graphic very similar to this from me previously. Apologies that the emissions data is starting to get dated, but the point is still the same. Pennsylvania, when you look at our economy and the businesses and the industries that we have, we make energy, we generate power, we make concrete, steel, hydrocarbons, pulp and paper, chemicals, etc. So we've got multiple categories of CO2 emissions all over the state. And for that reason, we're a big part of the problem. So we need to lean into this challenge of climate change mitigation. Okay, so on to my next piece. What do we mean by geologic storage, and why might that be important as a piece of the solution? So geologic storage involves the injection and placement of liquids or gases, so water, methane, natural gas, in other words, natural gas liquids, CO2, any product or any fluid, temporarily or on a permanent basis in one or more categories of storage containers. And there are three classes of geologic storage opportunities. Porous rocks, we have a lot of those here in Western PA in particular. We've got sedimentary rocks, sandstones, carbonates, siltstones. Salt caverns, these are situations where you have bedded salt or dome salt structures, and you can solution mine a cavern out of that material and use it to put your product in. We have salt caverns in New York. You probably heard about them down in the South, in the Gulf Coast region. The Strategic Petroleum Reserve is that. And then the third category would be mined or engineered caverns, where you take a hard rock, be it it could be an igneous rock, a granite, for example, like Marcus Hook out in southeastern Pennsylvania. Mine out a volume of a certain type, and then that becomes a cavern that you can mic up, so to speak. You can put your monitoring equipment in and make sure that it's a sealed situation. My point being that it is an engineered solution that you can go in and create the size and space. It's not a natural thing. The graphic that you're seeing on the right-hand side is a cartoon cross-section of sorts from one of the regional consortium projects that the state survey did back in 2016, 2017, where we were commissioned to evaluate the tri-state area's subsurface rocks for potential natural gas liquid storage. So we were commissioned to look at not just the siliciclastic sandstone porous rocks, but also bedded salts. In our case, the mined engineered cavern opportunity was limestone. So in general, that's what geologic storage is. You've got a good formation underground that has the engineering and volume characteristics that you need, and it will safely hold whatever you're injecting, be it a fluid or a gas. Another thing I wanted to hit on, because this is part of the discussion, Pennsylvania has a diverse geologic footprint and multiple geographic or physiographic provinces. And as you move from Lake Erie south and east across the Commonwealth, we go from generally flat-lying, relatively undisturbed sedimentary rocks in western PA and the northern tier counties. Once you hit the center part of the state, the valley and ridge, these are our, rocks that have been deformed and, they've been pushed up, and we've got the mountainous areas of the state. And as you go farther, the south and east, you end up in the Piedmont and New England provinces, and these tend to be more igneous metamorphic rocks. So we've got all types of rocks. It's the Appalachian Basin part of our state, though, that has been the focus of the survey and the DOE's research over the past 20 years. More specifically, I wanted to, so in this map, I've turned on all of the rocks that have been productive of oil and gas for the past century and a half. And so the different colors are just showing you where shallow and deep oil and gas have been developed, including coal bed methane, which is more specific to southwestern PA, and then our shale gas resources, which we have along the Lake Erie shoreline, as well as throughout the state, southwestern and northeastern PA, with our Marcellus play. And there's also Utica and other so-called upper Devonian resources as well that have been produced for gas. Make a note of the dark brown polygons that you see in this map, because from southwesternmost Pennsylvania, Greene County, up through Tioga County in north central PA, those brown elongated, in many cases, polygons represent natural gas storage fields. So that's methane that's being stored underground by utilities for seasonal storage and seasonal withdrawal. Showing the natural gas storage fields areas another way, courtesy of the DEP's website. The municipalities that have natural gas storage fields are shown here in blue. So the storage of natural gas in Pennsylvania dates back to the late 1930s. So it's been happening for almost a century. Most of the formations that are storing natural gas tend to be sandstones of Devonian age, and some are shallower than others. There are some storage fields, I'm going to show you some graphics, that have stack storage where different formations are both used in concert to store natural gas within the footprint of the storage field. And in other places, they're very specific to, let's say, the Oriskany sandstone on an anticlinal structure, within a very precise footprint. So as a geologist, we look at oil and gas activity, and we map where the wells are, what they're producing from, and track not just the logistics of that process, but also interpreting the subsurface geology with information from those well records. So when I go into my GIS and I pull up our fields and pools, our oil and gas fields are marked with red lines. So those are the bold red lines you see, and then all the dots, those are wells. Those are existing oil and gas wells here in the Commonwealth. This particular snippet comes from Westmoreland County, southwestern PA, and the Oakford Field. So the light blue highlights are pools of porous sandstones that have been repurposed for natural gas storage over time. So they originally were producing natural gas, and then at some point switched to injection mode, and the utilities using them for seasonal storage. So the one in the center of the screen now, that's the what we refer to as the Oakford storage field. It's 9 miles wide. It's actually storing gas in both the Murraysville sandstone, which is the top of the Devonian here in southwestern PA, and the Fifth sandstone, which is the base of the Venango group, if you know those terms. Let me go to there's another light blue highlighted area in the top corner of the site. Oh, shoot. Okay, I've got a Google map for you showing this is the area of the field. With Google Maps, you can't necessarily, you're not going to see the wells at this level, but just in case you're, from the area and you can see the general lay of the land and the roads, Route 22 kind of goes west to east across the screen. So when I look at that other little blob of storage area, this is the Clugston field, and the storage here is in the rocks that comprise the 100-foot zone of the top of the Venango group. This particular storage pool is just west of Westmoreland, so it's in easternmost Allegheny County. And when I show you the Google map, many of you will recognize this. If you drive along 22, you can see this Dominion storage facility. So if you want to try to visualize what gas storage or what product storage sites might look like, this is my best local example. Obviously, we do not have any currently operating or active CO2 storage sites or anything related to that. So this would be my best analog to show you. And then the third piece I wanted to do is bridge the gap between, the technology and the technical understanding of all this, and then how does this fit into Pennsylvania? Why should we care? How we might think about preparing and being part of the energy transition in this way, using CCUS technologies. So here's another picture of Pennsylvania, right? I've got some shading. The Appalachian Basin, the sedimentary rocks of western and north central PA we've got a white background so that I can show you all of the shallow and deep oil and gas, as well as natural gas storage pools. So this tells you where we have our existing subsurface geologic information to work from, right? So it's on the plateau. We get, by virtue of the oil and gas industry doing their business here and having it regulated by our DEP colleagues, they submit reporting and geophysical logs and information to the state. We consume that, interpret that, and we can talk about our subsurface geologic formations and what prospects they may be. The colored boundaries of these pools that I'm showing you aren't necessarily the limit of the potential geologic resource. It could be farther or a bigger footprint than what I'm showing, but you get the idea of where we're looking at. And we do know the least about our deepest rocks. The Rome Trough is a deep basinal structure at the bottom of the sedimentary section, and we expect that it's deepest in southwestern PA. So there's places here, I'm coming to you from Pittsburgh, the depth to basement may very likely be in excess of 20,000 feet beneath our feet. The most common denominator for a depth range of where we have good data control is that first mile, because it doesn't cost as much to drill shallow wells. And early on in the oil and gas industry, of course, they're only going to drill to the first occurrence of oil, right, and produce that. And as time passes, as the industry evolved, as technology got better, improved, et cetera, directional drilling, fast forward to modern shale gas plays here in the state. We have gone deeper as the industry has gone deeper, but still that deepest part of the subsurface we know the least about. So just for the sake of giving you a sense of scale of potential, carbon storage estimates. This is something that we, along with our sister geologic surveys throughout the basin and across our Midwest regional partnership area, have evaluated and used the DOE methodologies for estimating the carbon storage capacity of different formations. What I've done here, I'm showing you on the map. There's not as much color because what I've done is I've grouped our rocks into carbon storage systems of sorts, so chunks, whole intervals of rock that represent cap rock with reservoirs, and it roughly delineated by age here. But when you do that exercise, and based on our field and pool level reservoir data that we prepared for MRCSP, this is the number crunching that we get. So certainly the shallowest reservoirs, we tend to have more of them. As you go deeper, you have less reservoirs, right? But there's thousands of, around 2,800, 2,900 potential pooled areas that could be looked at for storage. When we use the DOE's calculation approach to come up with a mode storage estimate, I'm showing you the numbers here, but the tabulation is the equivalent of, these are metric tons, and with the zeros, orders of magnitude, it's like 2.4 billion metric tons. That is an estimate. That is not, so in other words, that is the total potential resource, but still we need the industry to go out and prove those resources to make that switch from resource to reserve. And that continuum of evaluation has to happen. And as industry potentially pursues projects here in the state, they, based on their risk tolerance, their business models, their capital expenditure possibilities, all those things are going to come into, is this a resource or a reserve for us? And does it store enough for what we're going to do, what our industrial product might be in terms of emissions? So it's a different answer for everybody. I just want to make sure that we all understand I'm talking about storage estimates of a resource. It would still, you would still need to prove your resource at any given carbon storage project site. To give you the sense of scale, what 2.4 billion metric tons is equivalent to, EPA has a web-based calendar that's interesting, and so I plugged my total into that, and that volume is equivalent to 510 million passenger vehicles being driven for a year, and whatever their emissions are, it's equivalent to that. It's equivalent to the amount of carbon that can be sequestered by 3.1 billion acres of U.S. forests in 1 year's time. Or if you want to think about planting trees, 39.7 billion tree seedlings planted and then grown for 10 years. So it's geologic sequestration in terms of scale of opportunity. It's pretty substantial. Now, this stuff is not, I'm not talking about CCUS in a vacuum or in some kind of academic way. This has actually been done across our country and internationally as well for decades. I will say first that the injection of CO2 for enhanced recovery of hydrocarbons is the longest acting application of CO2 injection in the Permian Basin of West Texas, and we're 50 plus years of doing that work. So the industry is used to capture, taking gas and injecting it underground. It's not a new process by any means. Internationally, there have been permanent storage projects, particularly offshore. If you think about the North Sea activities, in excess of 20 years. And so back to the United States, the Department of Energy's Regional Carbon Sequestration Partnerships Program, of which PA and neighboring states, we were part of the Midwest group. We were one of 7 regional partnerships funded between 2003 and roughly, well, depending on the partnership, almost 20 years, so fast forward to like 2021, let's say in our case. And each one of those 7 partnerships had to, as a condition of their funding and their project, complete a full-scale CO2 injection project. Our partnership had the project in the Michigan Basin, so the westernmost part of our partnership region, and all the other partnerships had to inject at least 1 million metric tons in a formation or formations of their, in association with their scoped out work. I say all that to point out that there are best practice manuals now based on that real world experience of projects here domestically within the last 2 decades, warts and all, good, bad, or otherwise. And the best practice manuals were written by the researchers and the lessons learned. So we have these things to lean on. You'll have access to my slides. So there's web links on the next couple of slides to talk about that more. So if we think about the relatively flat-lying sedimentary rocks of the Appalachian Plateaus, currently this cartoon cross-section, which many of you are familiar with because I've used it for some time, we've got a lot of extractive industry. There's shallow and deep oil and gas production. There's coal bed methane production in advance of longwall mining. There's shale gas development. If we were to, now, unlike other regions of the country, our basin, the Appalachian Basin, is not it's a productive basin. And so whereas other basins don't have to worry about coordinating activities, we would, and we will. The coordination of taking stuff out of the ground and then putting CO2 or wastewater, all that stuff has to be reconciled. And so some of the terms you see here are the terms that you may read about in proposed projects. But just like our DEP colleagues coordinate the extraction of coal and natural gas here in southwestern PA, for example, the coordination of geologic storage and extractive activity is going to have to be, something that we live with for some time. Now, this last little bit, I want to give props to Andrea Mullen, one of our colleagues at DEP, who's part of our interagency work group. She provided a great EPA UIC presentation to our group a couple years ago. So I'm borrowing her slides. Thank you, Andrea, and Tom, and everybody in that group that's been so helpful to us. We currently, as the Commonwealth, have injection wells now. Injection wells for wastewater, they exist among producing wells. So the cartoon here shows that, there's conventional wells, there's natural gas storage, there's unconventional activity. So those things coexist even now. And as of the time of this particular presentation, there were, so a couple years ago, there were 11 active Class 2 wastewater injection wells in the Commonwealth. They tend to, and they have certain requirements, of course, for the steel and the casing and, the depths and nesting requirements, depending on what they're going through. It's just a long way of saying that those injection wells can and have been drilled and are being used here in the state and the larger region as well as we go west and west to Ohio in particular. Now, Class 2 versus Class 6 wells, hear the underground injection control program speak from EPA or read about it. The class 2 wells, so you've got a caricature on the left here. Those are set up to receive oil-filled brines or be used for enhanced recovery of hydrocarbons from the subsurface. Whereas class 6 is a different beast altogether and has a more stringent, detailed set of requirements to propose and get approved. I would encourage everybody to have a look at EPA's website. They do explain all of the UIC well classes 1 through 6, and the class 6 wells used for geologic sequestration of carbon dioxide have very specific requirements, and there's very detailed, thorough data set review modeling that has to be included as part of the application process. So as EPA and or the states that have primacy go to review that, it takes them a while to do so. But you can go to their website and see the list of wells there's currently 2 active class 6 wells, a couple more that were used, but the projects are over, and then there's a whole bunch that are in process for being reviewed within a 24-month time frame. And then this graphic is just another way of showing that once an entity submits a class 6 permit application, EPA and states with primacy, which Pennsylvania is looking to seek, that would go through various steps and before they issue a determination to give the permit approval or not. That is my time. Again, you'll have my slides after this. Meredith will make sure that everybody gets that. And looking forward to the discussion. I'm going to stop sharing because I've got colleagues here who want to take us through the rest of the discussion. Thank you.
Thank you, Chris. I appreciate in particular your Dominion example. I've driven past that many times on 22, so that really put me in a better understanding, gave some context. I do want to take a minute to ask a couple questions. We're getting several questions from the audience. Thank you, folks. We'll try to answer all of them as we can. One quick one, how does the CO2 storage potential compare to annual CO2 emissions in Pennsylvania?
So, yes, I have to think about that. I'm not sure that I'm going to remember what our annual emissions are. I do know that we're like in the top 5 states in terms of our annual emissions in the United States. So we are big, as I said, a big part of the problem, but historically because of our power plants. So we have had the coal-fired power plants beginning to be, they're aging out, so they're being retired. But still all the other industry continues. It still would be, now again, if all of those estimated storage resources would be proved out, which we don't expect that, the 100% is never the thing. It would still be, I would say, at least 100 years or more, and that's just an estimate. And again, if everything was in the ground and could be utilized fully without interruption, so a century or more. Yeah.
Okay, it sounds like we are a big player in the emissions profile of the country, but the potential to be a big part of the solution as well. Another quick one, and then maybe we'll turn on to the next presenter, is the resource estimate, I believe this was in one of your slides, of 2.4 billion metric tons exclusive of the natural gas storage fields that are already being used in Pennsylvania.
Yes. And in fact, that estimate is also conservative because we did not include shale gas reservoirs. We did not include conventional reservoirs above a half-a-mile depth because carbon dioxide, any gas has a supercritical point, and in the case of CO2, to make it its most dense viscous state or supercritical state, you need to be, generally speaking, about 2,600 feet below ground. So the shallow stuff did not include, and the shales we did not include, even though shales may have some good potential for CO2 storage because of the mineral surface chemistry. So yes.
Okay, great. We have a question about comparing numbers of class 2 wells. I know that if you were to look online and look at EPA websites, you might be able to find some data and just do a quick comparison. Someone posted a reference to the annual greenhouse gas emissions inventory from DEP's website. Thank you, that's helpful. And in
Yes,
response
thanks,
to the
Karen.
question about the volume of gas that we need to store. And someone asked, and I'll make this our last question, then we'll turn it over to Jackie. Would it be feasible to drill down through a carbon storage area to, for example, access a lower formation for extraction? And this person refers to West Virginia and other states allowing this. Just curious, what are the technical challenges to avoid leakage here? That sort of question. Does that sound like a question you can answer?
It's a very legitimate question. It's a great question. I've often thought about the opposite, where if the industry is continuing to develop the Marcellus, let's say, and the deeper, maybe Camber Ordovician rocks turn out to be a good sink for a project and industry in one part or another of our state, they would have to coordinate going through the extractive reservoir to get to the storage. And for permanent storage, we tend to want to go deeper, and use the deep saline or depleted, in our case, depleted oil and gas reservoirs as the reservoir. And I'm not a petroleum engineer, but I know that would be something that you'd have to coordinate, not just the timing of, but the well construction, spacing, and probably some other things that I'm not even aware of. So yes, that is one of the challenges.
Okay, great. Thank you, Chris. Yeah. With that, we'll turn it over to Jackie.
Hi, Meredith and all. Hope everyone's doing well. Thank you again for the opportunity to talk with you today. I am going to share my screen here. Meredith, are you able to see that? Could you please confirm?
Yes, you're
okay,
good to go.
Great, thank you. Thank you. Again, my name is Jackie Fiddler. I'm Vice President of Environmental and Sustainability at CONSOL Energy, and today I'm going to tell you a little bit more about our advanced PFBC power plant project. For those of you who are not familiar with our company, CONSOL Energy has been mining coal throughout the Appalachian Basin for more than 150 years. We like to say, we have a very strong legacy, very proud of the last 150 years, and we ask ourselves, really, what does the next 150 years look like? We have almost 2,000 employees. As a result of our business, we estimate that there's approximately 5,600 indirect jobs. We're the largest private employer in Greene County, and our median annual employee compensation is $115,000 per year. So we have a very large footprint in Pennsylvania. Our Pennsylvania mining complex is the largest producing underground coal mining complex in North America. Our other assets include our Baltimore terminal and also a new metallurgical mine that we opened last year in Wyoming County, West Virginia. We like to say our legacy is built on our core values of safety, compliance, and continuous improvement, but our future is really based on efficiency, technology, and innovation. So when you hear from us, we recognize there's a large emphasis on ESG, At Consol Energy, we don't talk about ESG without talking about innovation. And so from our perspective, we refer to it as ESGI. And it's really that goal to be innovative and look for the future that has inspired our work on our advanced PFBC power plant project and also our investigation of carbon capture opportunities in Pennsylvania. Not unlike Chris, I will take a very quick opportunity to give some background context on, why this is important as the world, transitions or transforms and the economy, looks toward electrification and tries to address greenhouse gas emissions. Globally, in 2022, coal was still the largest source of electricity generation in the world, accounting for 35%. In the United States, coal-fired electric generation accounted for 20% of all electric generation. So coal continues to be, a primary source of energy for the world, and as well as a considerable source for the United States. Similar to Chris, we take a look at the IEA's scenarios for what does it take to get to a net zero future, not just looking at the United States, but looking on a global scale. And when you look at the IEA's scenarios for coal into the future, every scenario, whether it be the stated policies scenario, the alternative announced policy scenario, or the net zero scenario, each scenario acknowledges that coal will continue to be used. 2022 coal demand globally exceeded over 8 billion tons. If you look at the alternative policy scenario, you're approaching in 2040 still 2.5 billion tons of coal being used. However, a large proportion of that is going to be, those emissions will be controlled with CCUS. So even in the net zero scenario in 2050, there is still demand for coal throughout the world. However, 90% of the coal will require CCUS. From a social perspective, I think it's good to remind everyone that 774 million people still lack access to electricity worldwide. And since 2000, coal-fired electricity has been the broadest, largest source of supplying access to electricity across the globe. In order for coal to continue to do that, and in order to continue to meet that moral obligation to provide, emerging economies with access to electricity, coal's going to continue to be needed. And I think abated coal, especially in geographies where renewables are not ideal, this creates, renewables will be challenged to meet the demand, and coal will be able to supply some of that demand, especially when advanced technologies like carbon capture and storage are applied. As I mentioned, to us, innovation is really important, and we've looked at innovating throughout the entire coal value chain, starting with our coal mines, where we are looking at methane mitigation, at our coal preparation plant, looking at opportunities to reduce the amount of waste that we generate or reuse that waste coal, developing waste coal or coal into alternative products that are not combusted. Through that. And ultimately looking at advanced emission control technologies. And so our 21st Century Power Plant project was really designed to kind of bring all of these innovation efforts together. So what is the project? The project's been going on since really 2006, when we had designed a 1 megawatt pilot scale demo. It is conceptually a coal-fired power plant that will be fueled with waste coal and biomass. The current design stands at approximately 360 megawatts. We completed a conceptual design in 2018, and in phase 2 of the project in 2020, we completed a preliminary engineering design. We then moved on to phase 3 of the project, which we're currently in, which is completing a full front-end engineering and design for the plant. I want to acknowledge DOE's support of this project, which really has made all of this work possible. And also you'll see we have a number of team members who are working with us, including the Pennsylvania Geological Survey and the West Virginia Geological Survey. In addition to a number of technology vendors, we've really built a world-class team looking at this project. So our intent is to equip the power plant with a CO2 capture system that's capable of capturing 97%. Because of the co-firing with the biomass, the plant is going to be designed to achieve net negative CO2 emissions. It has been designed to include all of the emission control technologies, state of the art for the criteria pollutants. So we like to say that the plant is essentially very low to no air emissions for criteria pollutants, in addition to being its net negative CO2. It's designed to have a zero liquid discharge to the extent we can reuse impacted waters. For the plant, we're looking at, that as an opportunity to further reduce its footprint. And as I mentioned, this technology has been developed and something we've been working on since really 2006. So in this phase 3 of the project, we're looking to confirm that we can really permanently sequester up to 3 million tons of CO2 per year, ideally looking in Southwest Pennsylvania or West Virginia. Our primary thought was that we would site this plant at our Pennsylvania mining complex, which is located in Greene County, but spans, from north almost to Washington, PA, south, almost toward the Kirby area. So we cover a large footprint, and we would like to be able to site this plant in the vicinity of our operation, where we'd be supplying a low to no cost source of fuel. And also to the extent that we've identified great opportunities for CO2 storage within the vicinity of our operation. Another benefit of siting the plant in Southwest PA for us is in part due to our large surface acreage ownership position in the area. So with the biomass component of the project, we would establish one of the largest bioenergy with carbon capture and storage operations to date. For perspective, we envision cultivating 25,000 to 30,000 acres of biomass for this project, and we would deliver up to 300 to 500 tons of biomass per day to this facility. So on to the really interesting parts of the plan, and really some of the focus of today's conversation is about the CO2 capture side of the plant. So in this engineering phase of the study, we've selected 2 technology vendors that would provide us with detailed designs and cost estimates for the CO2 capture part of the power plant. So this would be the system that actually captures the gas and prepares the gas to be ready for disposition into a pipeline or into a CO2 well for underground storage. So we selected 2 technology vendors. Both vendors' technology is commercially available. We were looking for something that is an amine liquid-based capture system. We were looking for systems that had high technology readiness levels of 7 or higher, so we could feel confident that these systems would be ready to be deployed should this plant become a reality. As I mentioned, the 97% or better capture level was a goal for us. However, we also completed evaluations of whether or not we could what if the capture system didn't achieve a 97% success capture rate? Could we look at 90 or 95, for instance? And how would we have to adjust the biomass feed to the plant to maintain a neutral or net negative CO2 performance for the plant? So we've been very pleased with the results. However, I will say, for perspective, the CO2 capture system is very technically complex, and it's also very expensive. So when you look at a system from capture all the way to disposition, I would say operation of the capture system is almost 2/3 of the cost, from CO2 collection to disposition. So it's a substantial cost. It takes a lot of energy. And again, it just creates some challenges in real life to bring those costs down for us. Just again, from like a chemistry perspective, I don't know how much everyone understands about, what happens once the gas is captured. And what it does is the amine solution essentially isolates the CO2 and then compresses it into, we then compress the gas at very, very high pressure, and I would say a moderately high temperature, into a supercritical liquid phase, using very large compressors. So once the gas is in a supercritical phase, then it can be transported into, hopefully a deep underground rock formation that is porous and permeable. So there is a chemistry process that happens with that amine solution, and then followed by compression prior to transport. So this is a pretty intense process and an expensive part of operating these types of facilities. The other really exciting part of our project in phase 2 was really looking to characterize the CO2 storage capacity and potential within the vicinity of the Pennsylvania mining complex. And we were also challenging our project team to help us identify a storage area that could provide CO2 storage for the life of our power plant, which was estimated to be 20 to 25 years or more. So we're looking for a reservoir that could handle, 60 to 75 million tons of CO2 over an extended period. So our project team, initially looked at characterizing, if you look on the left side of the screen, we looked at an area that was within a 25-mile vicinity of the PAMC, but we ended up expanding the search area to 100 square miles, within 100 square miles of the PAMC. So you'll see that our search area really identified, a large portion in Pennsylvania that we characterized, as well as smaller portions in West Virginia and Ohio as well. I think some of the challenges that we were brought to our team is that, there are very few deep vertical wells in Southwest Pennsylvania that we could use to give us some confidence in terms of what the CO2 storage potential really is. There had not been any CO2 injection tests in Pennsylvania. As Chris mentioned, there are relatively few Class 2 injection wells in the Commonwealth. So what our project team did was evaluated existing seismic surveys to address different geologic and geotechnical data gaps. They also were looking at opportunities to stack CO2 storage potential as needed or if needed to, achieve that very high volume storage goal. So for the project to become a commercial reality, it really required local CO2 sequestration storage areas. And, there's a lot of exciting opportunities in Pennsylvania and within this tri-state region, and exciting talk about the development of hubs. So we envision our CO2 storage within the southwest area of the state to potentially become part of an emerging CCUS infrastructure. As Chris mentioned, the deep geology in the Ohio River Valley, particularly in Southwest PA, has good potential, but it's not been characterized. Within our area of focus, thick sequences of very, very Paleozoic age sedimentary rocks were present. And these are areas that have been utilized for hydrocarbon production, natural gas storage fields, and coal mining. These formations we determined are thicker in the eastern portion of the Appalachian Basin, where they're more than 25,000 feet. Multiple formations within the area, however, were identified as potential injection reservoirs, where low permeability opportunities could be used for injection. As I mentioned, our characterization efforts have really been looking at either very deep saline formations, and ultimately we also ended up evaluating some opportunities for reusing depleted oil and gas wells as another option for storage. We ultimately did land on identifying 2 potential areas that were targeted for storage. One is very close within the vicinity of our Pennsylvania mining complex. The second area is a little bit farther away, but still within a decent range of where we had planned to site our facility. There is a lot of considerations on both sites related to current land use, whether or not for that second site, whether or not transportation would be feasible, what would be required to get our gas from the plant to our secondary site. I also wanted to kind of give some perspective on, what does the storage site look like. We actually have designed a test facility whereby we would drill and test a 15,000 to 20,000 foot deep well in both of these areas that could potentially provide some critical information to help us characterize CO2 resources, injection capacity, and storage security. So we are looking at, we've identified a couple of areas. We're looking at potentially what could that next step be in terms of really characterizing the areas to give us some level of certainty that, these projects are feasible and that the storage potential is really as good as what we think of based on some of our desktop analysis and modeling. Again, as I mentioned, the economics of these projects are really driven by the 45Q tax credits and really heavily influenced by the CO2 capture and ultimately what would be that final disposition strategy. For perspective, since we started really heavily engineering this facility in 2020, the capital costs due to the inflationary environment and some other post-COVID macroeconomic conditions, the capital cost of these facilities has nearly doubled since 2020. So we need to definitely have some more certainty and some additional work done before we can make, a firm decision on whether or not this project makes economic sense for us. or ultimately for our other stakeholders, and would also, as I mentioned, really heavily depend on support from the federal government, and particularly the viability of the 45Q tax credit. As we mentioned, that the number of sources for CO2 in Appalachia are large, as this figure shows, and that there will be a lot of competition for storage opportunities. And I think we see that, as an opportunity from a business standpoint, but also something from a competitive standpoint for us all to be aware of. So again, we're very proud. We're going to continue to move forward with phase 2 of the project. And we're going to try to reduce some of that uncertainty, potentially look for opportunities to maybe do some field work should a funding opportunity arise that could help us offset some of those costs to really perform some good characterization work in the field. So when we were looking at our study, we had 4 goals really in the last year and a half, and one was to identify viable CO2 disposition options, and we did feel like we achieved that goal. Our second goal was to complete an environmental information volume where we defined some of the community socioeconomic, regulatory, health, and safety factors for constructing this type of facility. We've completed that, and we believe there is a likelihood of success. We performed a life cycle analysis to confirm that we can really achieve net neutral or negative CO2 emissions. And, we did update the investment case. While the economics are not as favorable as we had hoped, we have identified specific areas for us to work on, as we continue this project. As I mentioned, we're very thrilled with the opportunity from a CO2 perspective. We have really developed significant knowledge and understanding through the extensive data analysis that was done by our project team, looking at opportunities in Appalachia and particularly here in Southwest PA. I did want to end on just a positive note on, being a large company operating in Pennsylvania. We do think there's a lot of great, factors that Pennsylvania can leverage: our workforce, the fact that we can continue to have very long-term family sustaining jobs that, industry has traditionally brought to the Commonwealth. As Chris mentioned, some of our partners, especially in the DEP, have incredible expertise on mining, oil and gas, compliance and permitting, and we believe that the regulatory framework for implementing these types of projects really exists, and making sure that it's done safely is really there. As Chris mentioned, we need to work collectively to support efforts to advance the regulatory framework so that these types of projects can really become a reality, and make sure that, as I mentioned, the economics continue to be favorable or become more favorable to make these really a reality. I will end there, and thank you again for the opportunity, Meredith.
Thank you, Jackie. We appreciate your perspective. And I think we're a little bit behind, so I'm going to direct Jackie and Chris, if they would, to the chat box. There may be questions that you can answer quickly just by typing for us. And if we have time at the end, we'll try to circle back to them. I just want to make sure we have enough time for Perry. Perry, are you with us? It's your turn.
I am definitely here. Can you hear me?
Yes, sir. Thank you very much.
I look like I'm in a jail cell with the background, but I'm actually in an airport. I apologize. Travel schedules got confused, and I found, I believe, the quietest place I can at Pittsburgh Airport in a corner here. But it's very much an honor to be here and to share a panel with Chris and Jackie. I'm taking notes the whole time that both are talking, and I'm sure it's been valuable to you also. I'm tasked with sharing about the business case for carbon capture storage in Pennsylvania and Appalachia. And I'll share my read just a couple of slides because I really want to mostly just have a conversation about. Sorry, my browser is slow here. All of a sudden, let me see if it'll work this way. If I just use this other screen, there we go. Are you able to see those slides?
Yes, you're good to go.
Okay, super. So you might have heard about the Key State project and some of the history behind it. Essentially, my partners came to me with a 7,000-acre stranded gas asset, meaning it wasn't pipelines to the 7,000. One owner, private owner, very remote site that the family had for several decades collected parcels of land with the ambition of starting some kind of commerce in that area. It was formerly a coal mining area, and they could see the decline coming beginning back in the 70s. And really, we're fulfilling some of their vision. So a little bit about Key State Energy. So we've designed a template based on the Pennsylvania site in Clinton County, where we've integrated natural gas extraction, reforming the natural gas, storing the CO2 on site, generating power on site, and making a portfolio of products that have an advantage on proximity to market. We have a second site in Virginia that very similar dynamics, former coal mine area, just huge job loss the last decade, and a ready workforce, but really challenged by a lot of the classic Appalachia issues and declines. And so, a core of our goal is to can we make a business case out of energy transition? You can't sustain yourself over time unless there's a business case to it. And incentives for research and early risk capital is vital, but you have to have a business case. And so essentially we were looking to displace a higher carbon, higher cost product with a lower carbon, lower cost product. And that's really where we need to get to have a successful energy transition. And doing that specifically, our goal became to be able to make a zero emission hydrogen as a fuel and used for other products that's affordable. A lot of challenges around cost of hydrogen, but also that's widely available. And thus the vision for this Atlantic Coast corridor came about. And essentially, we're following the geology in the placement of these facilities and following the natural gas feedstock supply and anticipate another facility to be planned back in Pennsylvania the latter part of the decade, and then perhaps another one or two outside of Appalachia. So the products that we make, and really the value proposition from carbon capture storage is how taking and decarbonizing, remediating natural gas as a feedstock or whatever process you're working on, how it increases the value of that end product. And that's exactly what it is in our case, that remediating natural gas and reforming the natural gas and separating the C from the H and the CH4 methane, we have a very valuable hydrogen fuel product, extremely low CI score, and that has all the potential and uses that you've heard described recently. You use hydrogen then to make ammonia, and then likewise that has the same carbon intensity. You've already captured the carbon on the front end of the process. In our case, well above 99% of the CO2 is captured as part of the chemical process at the beginning of the facility. We're not capturing a flue gas, it's not combusted, and that has to be captured. So we make ammonia, and then thirdly, we make urea, which can be used for fertilizer, and which we'll use fertilizer in Virginia, that project, but we'll use for diesel exhaust treatment in Pennsylvania, which is just a humongous impact NOx emission remediation has had since the early 2000s when it was required as part of the exhaust system for diesel trucks. And I apologize for the background noise. Maybe you can't hear it, but it's very loud here. So just a couple more points, and then I really get to the specifics of the business case. Our America, fortunately, we have an innovative view and ethos, and we really are a both and kind of society, and with technology and a lot of hard work, we really can have historic emissions reductions along with historic job creations, and particularly job creation in areas that have been in decline, in opportunity, underinvestment for decades in some cases, and certainly these type of facilities, $2 billion facilities, will have just enormous economic impact and job creation on these areas. And to that case, and to illustrate it, these areas have been identified by the Appalachian Regional Commission as particularly distressed related to energy transition, the decline of certain industries, coal, steel, et cetera. And our facilities set right in those areas, and some of which have been identified in the recent administration and characterized as coal community, transition communities, economic revitalization community goals, et cetera. And we lie within those. So our site specifically, and fortunately in our case, is very remote, on private lands, miles from state land, certainly state forest lands, but a 7,000 acre, one owner, contiguous tract of land in our 240 acre manufacturing site, of which we'll use about 35 acres for the facility itself, sits in the middle of this tract. So it's very, very good from the standpoint of building a gas synthesis process because we don't have neighbors to bother. Or there's 16 registered voters in West Keating Township that the facility will set. So we'll have huge impact in the 4 counties, job-wise, et cetera, spin-off industries, et cetera. But fortunately, we're not close to people, homes or businesses that will have impact that would be challenging. Let me quickly go to this study was done by PA Manufacturers Association maybe 4 years ago. At that point, our facility was focused on fertilizer, about a $500 million facility. And the job numbers are just enormous, job creation numbers and annual economic impact numbers enormous. And I grew up in a very rural county. I lived in State College for 40 years, but and I live in a rural area now. And I know, every time I look at slides like this, I tear up because I lived in those type of towns, a one industry kind of employer type of area. And I know what this is going to have an impact on jobs and tax base and new schools and YMCA and nonprofit donations, et cetera. There's huge impacts. So the same for Virginia. And I'll stop with this slide. I did want to just talk a little bit. We really are at a place as a nation where we can have both job creation that's not transitory. It's not just construction jobs or just well drilling jobs, but their jobs and they're valuable. I didn't mean to taking anything away from those. They're vital jobs. But along with that, the jobs created will be long term, well above sustaining level jobs. There's no minimum wage jobs anywhere within sight of a facility like this. And the impact that it'll have in both climate concerns and remediation of emissions and economic development, we really can bridge that now in the fossil energy economy, which we believe is shifting to a hydrogen economy. This combination of natural gas supply and very low carbon intensity reforming of natural gas to hydrogen with carbon capture and storage is going to make Appalachia a hydrogen superpower for the next 30, 40 years. We're honored and excited to be a part of that transition. So let me turn off my hearing and just talk to you for a second. So, I'm a person that's driven by passions often, and I have to be kind of pulled back to earth sometime. Of how can this be sustained? There's got to be a business case. You got to have products that there's a willing buyer, and if you don't have buyers, you have a science experiment, but you don't have a business. You have a hobby, but you have a nonprofit, but you can't sustain that. How do you make a business out of this? And really, it comes down to taking a feedstock and value adding to that feedstock by processing it somehow. If you have cotton, you value add by making a shirt out of that. In the case of natural gas, we're able to reform that and separate the C from the H. In our case, put the C back down the hole and use the H as a fuel directly to generate power directly, or to be used combined with nitrogen to make ammonia and other usable products that there's market for now. So it has to be a business case, and we need to make sure that our ambitions about and concerns about making a difference, creating jobs, climate remediation concerns, so has to have a business case somewhere. And really, ultimately, cheaper, better wins. And we've got to come to energy transition fuels, and that are both that. They're less expensive or equally expensive as legacy fuels, but are better and have lower emissions. I couldn't add one single word to what Chris has said to give a background understanding of the potential and the challenges of geological storage. It's expensive, it's very technical, but fortunately, the workforce that we have in Pennsylvania, the skills are transferable from the workers in natural gas and coal. Those same skills are what's needed to drill and to characterize geology for carbon storage, or to work inside of our kind of facility. Same kind of technical skills, work ethic, etc. So we're perfectly positioned in that standpoint for energy transition. And to the business case for landowners, the business case for municipalities, Chris mentioned there has to be a coordination between those who own the surface rights, which usually translates to they own the subsurface rights, also the pore space rights, storage rights, and then that has to be coordinated with those who own the mineral rights, again, natural gas production rights. And it might be the same party or separate parties. And unfortunately, there's a value proposition that each of those sets of parties, it makes a ton of sense for there to be coordination between those parties, because there's a value proposition for all these parties. Sorry, there's people coming and going. Again, I apologize for having to do this from the airport. And so to put in context for the landowner, there's a lease that's signed and a transaction for pore space rights, similar to rights in acquiring natural gas production rights. So there's usually a royalty, a purchase of the rights, and then some type of royalty ongoing or a fee for storage ongoing. So a good reference point in the Commonwealth is to look at how natural gas is stored. And historically, in the last number of years, that's usually a per acre fee that's paid, and then translating it to CO2 storage of per ton of what's actually injected fee paid to landowners based on the acres that they have within a certain field of where there's an expectation of the CO2 plume to go. So there's an opportunity for people to benefit in the same way if gas was being produced and they benefit from royalties, etc. One, I think I'm gonna stop and leave our time for questions and probably much more productive. Is that from our case, the small business owners in Pennsylvania, my partners have, they all went to Penn State, came back to Pennsylvania to start companies. We weren't looking to pick another state to go to. This was the asset and that we're placed where we were working. And so we're working to make this tract of land viable for this type of business. And how we can maximize the tract of land, make a product that has value, has a market and off-takers, and be able to have a sustaining business over time. And just one last comment I think I'll make it. Anytime a hydrogen ammonia facility is built in the U.S. historically, Europe historically, there are spin-off industries, related industries that spring up around it. And it creates a ecosystem of manufacturing around it. And so it's that roll-off effect. And most of projects that are related to carbon storage somehow, whether it's a power plant eventually that will store its emissions, or whether it's a manufacturer that will store its emissions, it is going to spawn other businesses and other related businesses, or other businesses needing CO2 storage space, and there's collaboration on that. The transport of that somehow, in our case, we don't have pipelines. We have to move it around as our own lands. But, there's a value proposition to landowners in that case, and in the moving as well as the storage of the CO2. So my role is to kind of give a little bit of the business perspective, the business case for the Commonwealth. But I think I'll stop and we'll have time for all of us to take some questions. Might be the most productive at this point, and maybe the quietest also.
Okay, thanks so much, Perry. And again, we appreciate you doing this from the airport. I'm going to share my slides. So this is our last chance for questions. I want to make sure I get to ask the panel a key question about barriers. If you could quickly, maybe one word or two, what kind of barriers, whether legal, regulatory, economic, political, social, what are the key barriers or the biggest challenges? What type of barriers are we looking at to making CCUS more widespread or more robust in Pennsylvania?
I can make one quick initial comment, and that is, I think that we need desperately a demonstration, a business case, a plant, a project that's a demonstration where we can bring, I don't mean on an experimental scale, but a business that's demonstrated. Once there's a facility where people can come to and see it being done and the dynamics around it, it's on then. That mystery is taken away at that point. It's like you being able to drive by the gas storage facility you mentioned, Meredith. It takes the mystery out of it. It begins good conversations around it. I think so. An example would help tremendously.
Chris or Jackie, any thoughts?
I'll just add really quickly, I think I agree with Perry, but to get there, I think the first thing we need to do is make sure we have the regulatory framework in place so that we could even permit and construct one of these facilities. But we, from an industry perspective, I think do have a job to do to, educate and outreach and make sure that these projects can be implemented, responsibly.
And then I would just add that, as I alluded to earlier, depending on where you're at in the country, some sedimentary basins are not hydrocarbon bearing. So the coordination and just the consideration of what do we want to use our rocks for? Does it make the most sense given our needs and our wants and just the logistical needs of our culture to store stuff as well as take stuff out? Or, are we looking at pipelines? What is the best and highest use of our geologic natural resources? And that is something that we at the survey, we really try to ground that discussion with the factual geologic data that we collect and we map for the good of the order.
Great. Thank you so much. We're out of time, so I'll just say a final thank you to everyone for participating. Thank you, Chris, Jackie, and Perry, so much for sharing your expertise and perspectives with us today. We certainly appreciate your time. And I have a final slide. I'd like to advertise part 2 of our webinar series about storing carbon in trees. So we'll have a group of foresters with us. If you have any follow-up questions or comments, I encourage you to visit the CONRAC website. We have a contact us form. And apologize that we weren't able to get to everyone's questions today. Our IT staff will put in the chat a registration form or link for part 2 and a link to our CONRAC website, if you would, Era, please. And we'll also send a follow-up email to all participants with information from today's program, including slides and links for our next event. Thank you so much. Have a great day.